Hello everybody. Today we are going to wrap up PORHEPCAC, which of course is Problem Observation, Research, Hypothesis, Experiment, and Procedure. We have spent the last few days talking about collecting data. Basically, the one thing I've never said about collecting data is how and where do we do that, and the answer is in a data table. So we've talked about how to use a ruler and many different aspects of collecting data, but where do we do it? We usually put it in a data table. Then we're going to talk about analyzing data. Basically, that can be summarized as putting it into some kind of chart or graph. And then we will talk about the 5 things that should be in your conclusion. So we are going to talk about analyzing data. That's the main part of today's notes. We'll usually make a chart or a graph. We may do it in a computer lab and actually use a computer program like Microsoft Excel, but there are some rules about making a graph, which is conveniently why I have this PowerPoint. So the main thing we need to talk about analyzing data is making a graph. So quickly, just don't even need to write this down, but just look at this data table and think about what kind of graph you think this should make, or we should use for this data table. Because there are 3 kinds of graphs or charts. What kind should this use? The answer is we should use a line graph to show this data because, well, we'll figure that out. Why do we use graphs? We use graphs to help us easily display information. If you have all your data in a data table, it's just a bunch of numbers unless you sit there and study it. And especially in some college level research, you may have thousands, hundreds of thousands, millions, billions of pieces of data, and that is just a bunch of numbers. But if you put it into a chart or a graph, it's easy to see. What are the types of graphs? Well, there are 3 main types of graphs. Please get these in your notes. The first type of graph is a bar graph. Bar graphs are used to show one-time results. On Tuesday, I asked all my friends what kind of food they liked, and here's the chart that I made, the graph I made. You're going to make a bar graph. Here would be an example. Hey, I asked all my friends their favorite kinds of foods, and it does not take but a second or 2 to see that pizza won. Most of my friends said they liked pizza. Well, spaghetti got the fewest votes, but it got more votes than a lot of stuff that didn't get any votes, so it's not that spaghetti is unpopular, it's just of the 5, it got the least amount of votes, but pizza got the most, with chicken second, hamburger third, turkey 4th, and spaghetti last. But, like I said, ahead of a lot of other things. One day you asked your friends this question, tomorrow you might even get a different answer, who knows? But in one time, these are the results you got. Next kind of graph, second of our 3, is a line graph. This shows changes over time. If you want to show change over time, you need to use a line graph. Students many times will get bar graph info and then connect it with a line. No. You need to use bar for one time, line for over time. So here's an example of this. The chart is named number of flip-flops sold per month. So over here is flip-flops. Over here is the number, or is the month. So we can see that The most flip-flops were sold in July. That shouldn't be a surprise. With August in 2nd and June in 3rd. What month is the lowest selling? You may first say March, but if you look very closely, it's December. December sold 0. So this shows, and we see it goes up in the summer, it goes down in the winter. And it starts to actually go up in March, April. Well, why? Well, I would say spring break. So line graphs show changes over time. And to be quite honest with you, probably the graph you will make most in science is a line graph. Not that the other two are useless and won't be used. The first lab we will probably do this year, we'll actually use the third kind of graph. And we will have reasons for making bar graphs, but line graphs are by far the most popular and most used in science. The final kind of graph is a pie graph. But I don't even like saying pie graph. That doesn't sound right. I like to say pie chart. So a pie chart or a pie graph is simply used to show percentages. And this chart shows the make of teachers' cars at Pike High School. As you could quickly see, this area is the most popular brand of car, and that is Toyota. The next most popular brand is this segment of the pie, and that is Honda. The next biggest segment is this right here, that is Ford. Then the next is actually a tie, 10% is Subaru and Chevy, and the smallest is this little sliver of the pie, Hyundai. When you make a pie graph, a pie chart, I always would split it into quarters so you know it's 25, 25, 25, 25, and then split those pieces up from there until you get your pieces to be about the right size. It may not be perfect, but you should be fairly close. We will be making a pie graph, I believe, in the very first lab we do. So, like I've said, we already know that we are going to make mainly line graphs. So here are how you do that. Here's how you make a line graph. First, set up your axes. First, you need to know which axis is which. There's the x-axis and there's the y-axis. The x-axis of a graph is the independent variable. This is the variable controlled by the experimenter. What can the scientist control? Well, a scientist can't control time, but a scientist can control how much time passes between when he or she takes data. So you can't stop time, but you can decide to write down an answer or a number every 5 seconds, every 30 seconds, every minute, every 2 minutes, every half hour, every hour. That time is most frequently on the independent variable. And since we're making a line graph, that's the one that will be on the x-axis. The dependent variable depends on the independent variable. So if we're talking temperature over time, time will be on the x, temperature will be on the y. Because as time goes on, the temperature goes up or down. The temperature depends on time. That's why it is set up the way it is. So here's a very simple graph. X is here, Y is here. And then, once again, if we are talking temperature and time, time should be down here. Temperature should be over there. So set up your x-axis, x and y axes, and label them. Then choose a scale. Here's a graph again. Always start at 0, 0. We will have 0, 0 right here. but figure out how far you could put these numbers. If this is the data table that we are about to graph, we don't want to put 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 could go all the way out here, because then we would only be using the graph, we'd only be using it up to here. We need to space this out. So we put numbers like this. Because if we go 1, 2, 3, 4, if we go one number every 2 lines, we can tell where half an hour is. We could tell where 1.5 hours is. We could even tell where 1 hour and 15 minutes is. It would be right here. And then on the y-axis, we could go every 5, every 2, but if we go every 2, we're going to run out of numbers. We go every 4. So notice, on this axis, I am going at 4 degrees Celsius every line. But on this one, I'm going half an hour every line, or 1 hour every 2 lines. That allows me to then chart this and plot my points and use quite a few of, it allows me to use most of my graph. If you don't use over half of your graph on the x-axis or over half of your graph on the y-axis, you aren't using your graph paper to the fullest of its capabilities. If we only went to 3, we wouldn't even be using 1/3 of this axis. And if we did this to, let's say, 100, then our biggest number is 22. We'd be way down here, and we wouldn't be using all the paper. So pick a scale that really fills out, but be consistent. If you're going to use 4 every line, make sure you go 4 every line, and make sure you don't run out of numbers. And then if you go 1 every other, go 1 every other. Don't go 1 and then 2. Don't skip around. Well, now, step 3, which will be on the next slide, is plot your data. If we go 114, 114 would be here, 220, 220 would be here, and 322, well, this is really easy. The way we have it would be right there. There's our data. Well, if this is a line, you need to then draw a line. So, and we will talk about this later. Is temperature something that's just going to be a straight line? No, it may go up and down. But we're going to do a lab at some point where it's going to be a straight line. And then we do what's called a line of best fit, but that's getting a little ahead of ourselves. This is going to be pretty because I'm doing this by hand, but you just want to put in and try to connect the dots as best you can. I didn't do it very well there, but forgive me. We can see that this is going up, and we can kind of even see that it's slowing down because it's curving downward. But we can see how that was supposed to go. So now, plot your data. Just said that. Give your graph a title. Titles can be creative. If you want to say hot and cold and have a Katy Perry song playing in the background, fine. But you don't have. You can be creative. If you simply want to be boring, boring gets the job done. And you want to say temperature versus time. Hey, I understand. But if it's temperature versus time of Coca-Cola or Pepsi or Gatorade, you want to say exactly what it is, please just give your graph a title. So to summarize our notes here on A, analyzing data, graphing, set up your Y and X axis, choose your scale, plot your data, give your graph a title. So then that takes us back to PORHEPCAC. We've now given it a title, done everything, Now we can write a conclusion, and this will wrap up PORHEPCAC. There should be 5 parts to your conclusion. First, make reference to your hypothesis. What did you say would happen? Quite frankly, you can simply copy your hypothesis and put it in your conclusion. I said, if blank, blah, 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 blank, then, that's all you have to do. Repeat your hypothesis. Number 2, say if you were correct or incorrect. Do not say right or wrong. Please say, my hypothesis was correct, my hypothesis was incorrect. And most of the time, you are going to be incorrect. But that's not a bad thing. Step 3, how far off were you? You said it was going to go up, it went down. You said it was going to be, you said you were off 3 degrees Celsius. You thought it was going to be 8, but it was actually 5. Say how far you were off compared to what really happened. Number 4, make reference to something of interest. For example, I thought it was interesting that temperature rose so quickly. In a span of 5 minutes, the temperature of the Coca-Cola increased by 72.4 degrees Celsius. There was a period of time when the temperature fluctuated between 101.3 and 101.9 degrees Celsius. The highest temperature was 102.0 degrees Celsius, and the lowest was negative 2.4. Say some things you learned. You know, you found it interesting. Don't say you didn't find anything interesting. What happened? Say what happened. And then this one tends to be the hardest thing, but even the best scientist in the world could probably do something better. Don't just say, I did everything perfectly. Say how you could have gotten better numbers. How could you have improved your accuracy? I believe that if we were to put the end of the thermometer in the Coke, that it would probably be a better accurate reading. We didn't do something right. We let the thermometer hit the bottom of the beaker, and that gave us bad numbers. What could you have done to do the lab better? And there is always an answer. That wraps up PORHEPCAC. Once you have finished these notes, we will be ready to do our first lab, and we will probably start our first lab. Thank you very much, and have a good day, evening, or whatever you have. Bye.